The sinc function is equal to the sine of x divided by x. As you might expect, just like sine itself, it oscillates about the x-axis, and it reaches its maximum value of 1 when x goes to 0. Its integral, now this is a little tricky, but it's known to equal pi. Let's multiply the integrand by sinc of x over 3. This changes the function, of course, but its integral, it's still pi. Multiply by sinc of x over 5. Again, it integrates to pi. Add another such factor, still pi. Another pi again. Add in one more term, what do you think? Pi or not pi? Well, it's pi, of course. And pi. Another. What? Welcome to Almost Sure. Now the Borwein integrals, well, they are definitely a bit weird and surprising. I mean, what kind of sequence goes like this? Pi, 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 0.99999999985 times pi. I mean, it's ridiculous. That's what it is. In fact, in their original paper describing these integrals, Borwein and Borwein, a father and son team, they explained how when a researcher verified these results by computer, he concluded that there must be a bug somewhere in the software. Now, I'm not the first YouTuber to discuss these integrals. In fact, 3Blue1Brown has a video, which is excellent, as always. However, my aim here is to show how this behavior can be explained with random or stochastic processes. And using this viewpoint, the behavior doesn't seem so weird at all. Maybe it even looks obvious. Maybe. And the Borwein integrals, well, they're just one example of a general phenomenon. So consider a stochastic process, S, and this starts with the value 0 at time 0. And then at time 1, it's uniformly distributed from minus a third plus a third. And then its increment from time 1 to time 2, this is uniform between minus a fifth and plus a fifth. And so on. So its increment to time 3 is uniform between minus a seventh and plus a seventh. Now the sequence of Borwein integrals, these are equal to pi times by the probability that this process S at the time n is less than 1 in absolute value. And for the first few values of n, it's impossible for the process to go beyond 1 because its increments don't even add up to 1. But as soon as the sum, 1 over 3 plus 1 over 5 plus so on, as soon as this exceeds 1, then our process can escape the range from minus 1 to plus 1, and our integral drops below pi. But I'm getting ahead of myself. Now I'll get back to Borwein's integrals in a moment, but first, consider this. How can we represent a probability distribution on the real numbers? Well, one way, and a common way, is to use a probability density function. The probability that a random variable x lies in a range between a and b, and this is equal to the integral of its density function from a to b. Then p must be non-negative, and as the total probability is 1, then p must integrate to 1. Now this only works for continuous distributions. Discrete ones, which take a finite or discrete set of values, they don't have a density function. But there is another way to represent any probability distribution, and that is using its characteristic function. So the characteristic function of a random variable x, this is just the expected value of e to the power of iux, and it's a function of this parameter u. Now, writing the expected value as an integral over the density function, then we can see that the characteristic function is just the Fourier transform of the probability density function. But let's try some examples, starting with a really simple distribution. A Rademacher random variable. Now this just takes two values, plus or minus 1, and with equal probability, so 50% probability for both minus 1 and plus 1. And its characteristic function, well, that's the expected value of e to the iux. This is the sum of e to the iu times plus 1 plus e to the iu times minus 1 multiplied by the probabilities, which are a half. And you may recognize this expression. It's the cosine of u. Let's try another example. Suppose x is uniform, so it's uniformly distributed from minus 1 to 1. And as this interval has width 2, the probability density must be a half on this range. So the characteristic function, well, this is 1/2 times by the integral of e to the iux from minus 1 to 1. And let's work this out. So the indefinite integral of this exponential, well, that's e to the iux divided by iu. And then we plug in the range, we get e to the iu minus e to the minus iu divided by 2u. Now again, this is a standard trigonometric expression for sine. So the characteristic function is sine u over u, or the sinc function. Let's try one more example. Suppose x now is uniform from minus n to n for some integer n. And I'll say x is an integer, so it's uniformly distributed over all the integers from minus n up to n. Now there's 2n plus 1 integers in this range, so the probability for each value is 1 over 2n plus 1. So we calculate the characteristic function, then we get the sum of e to the iux for all integers x in this range. And this can be summed using the standard formula for a geometric series. So let's do this. With a little bit of rearranging, we get this ratio, and both the numerator and denominator, these are standard trigonometric expressions again for sine. So we get a ratio of 2 sines. And actually this looks a little bit like sinc, as the sign in the denominator, well, it's roughly u when u is small, which well, this shouldn't surprise us because it's uniform, right? So it's a bit like the continuous uniform distribution we just looked at, except now it's discrete, since x can only take integer values. Okay, great. But why use the characteristic function? What's so fantastic about it? Well, for one thing, the characteristic function uniquely determines the distribution. In fact, if a random variable has probability density function, then we see its characteristic function is the Fourier transform of this. And we can apply the standard method of inverting Fourier transforms to recover the probability density. And if we do this, we get that the probability density, well, let's just look at 0. So the probability density at 0 is just the integral of the characteristic function divided by 2 pi. Okay, I mean, that's nice. But here's the really awesome thing about characteristic functions, which is what makes them super useful. And that is that the characteristic function of the sum of independent random variables, this is the product of their characteristic functions. Amazing, right? I mean, this is so useful because we so often have sums of independent random variables, and we can easily calculate characteristic functions from those for the individual random variables. And it's easy to prove. Just use the fact that the exponential of a sum is the product of the exponentials, And then the expected value of a product of independent terms is the product of their exponentials. Great. Now there's also a less interesting property, but still something that we need to know, and that is that if you scale a random variable by a constant, say you take random variable x and replace it by c times x for constant c, then this is the same as scaling the argument of the characteristic function by the same constant. Now let's apply this stuff. Take a sequence of independent random variables, which I'll call x of 0, x of 1, x of 2, and so on. And suppose that x of 0 is uniformly distributed between -1 and 1. And x of 1 is uniform from -1/3 to +1/3, and x of 2 from -1/5 to +1/5, and so on. Now, we know the characteristic function of x of 0. I mean, this is sine of u over u as we computed, or sinc of u. And by scaling, x of 1 has characteristic function sinc of u over 3. X of 2 has characteristic function sinc of u over 5, and so on. So let's look at the sums of these. So the sum s of n is equal to x of 0 plus x of 1 plus x of 2 up to x of n. Now, this is a stochastic process, but we know its characteristic functions. By independence, the characteristic function of s of n is the product, sinc of u times sinc of u over 3, sinc of u over 5, and so on, till we get to the nth term. Now, this is exactly as we had in Borwein's integrals, so let's circle back to those. So we have a stochastic process. S of n is equal to the sum of independent increments. We know what its characteristic function is. I mean, we just computed it. It's sinc of u times sinc of u over 3, and so on, up to sinc of u over 2n plus 1. Now, the integral of this characteristic function gives us the probability density of s of n at 0. Okay, I mean, that's good. But what is the probability density? How does that help us? We can work it out, but it's not intuitively obvious. But let me show you a cool trick here. Suppose we have the sum of independent random variables, x plus y, and we'll assume that x is uniform on some range from -a to +a for some positive value a. So that as this range has length 2a, the density of x is 1 over 2a on this interval. But the probability density of the sum of x plus y, well, this has a really nice form. Consider, how can x plus y be in some tiny interval from z or z to z plus dz? Well, the only way this can happen, as x is bounded between -a and a, is if y is less than distance a from z. And then x must be in the interval of z minus y to z minus y plus dz, which still has width dz. So, as it's uniformly distributed, the probability of this is dz over a, like so. And this shows that the probability density of x plus y at z is the probability that y is less than distance a from z divided by 2a. So the probability density at 0 is the probability that y is less than a in absolute value. Okay, this is much nicer. So let's go back to our process, s of n, and split out the first term. That's x of 0. So now we're just going to say s of n is the sum of x1 up to x of n. Now our integral that we're looking at, this is the probability density at 0 of x of 0 plus s of n. But x of 0 is uniform from -1 to 1. So as we saw, This probability density, well, is the probability that S of n is less than 1 in absolute value. So the integral of the characteristic function is 2 pi times this, or pi times by the probability that S of n is less than 1 in absolute value. Fantastic. After each increment, S of n increases by at most 1 over 2n plus 1. So the maximum it can increase is like 1 over 3 plus 1 over 5 and so on. But this series increases slowly, and it takes some time to reach 1. Summing 1 over 3 plus 1 over 5 all the way up to 1 over 13, it's still less than 1. So S of n still cannot exceed 1, and the integral is equal to pi. But once we get to the 1 over 15 term, then this sum, now it exceeds 1, so S of n has positive probability of exceeding 1, and the integral drops below pi. But it can only drop by a very small amount, right? This only happens when every single one of the increments x of 1 up to x of, 7, are very close to their extreme possibilities. So we get something which is not equal to pi, but is very close to it. Right, nice. I mean, that explains everything that we saw with Borwein's integrals. Now, in the explanation that I just gave, it didn't really matter that x of 1 was uniformly distributed. All that really mattered was the range that it could take, or the extreme values of the range. The fact that x of 1 can get close to 1 over 3 or minus 1 over 3, but couldn't exceed those values. Because all we really used was the range of values that the x's and their sums could take. So we can simplify this. Suppose x of 1 is equal to minus a third or plus a third with equal probability of a half for each. And x of 2 can equal minus a fifth or plus a fifth with 50% probability each, and so on. So now we have discrete distributions. And as these distributions could just take plus or minus some value, that's effectively what we call a Rademacher random variable, but scaled. We already computed the characteristic function of these. So if a random variable just takes values plus or minus 1 with 50% probability, then its characteristic function is the cosine. And then just by scaling this, x of 1 has characteristic function cosine of u over 3. X of 2 has characteristic function cosine of u over 5, and so on. Now, I'll still suppose that x of 0 is uniformly distributed continuously over the interval minus 1 to 1. So then the characteristic function of x of 0 plus S of n, well, this is sinc of u multiplied by cosine of u over 3 multiplied by cosine of u over 5 all the way up to cosine of u over 2n plus 1. And then in exactly the same way as we just did, we can say its integral is the probability that S of n is less than 1 in absolute value multiplied by pi. So for the first few values of n, this integrates to pi again, just like we had with Borwein's integrals. And then it's exactly the same thing once we get up to the cosine of u over 15 term, where n equals 7. Then S of n can now exceed 1, so the integral drops below pi. In fact, now we can compute its value pretty easily. The only way that S of n can exceed 1 is if each of the increments, x of 1, x of 2, up to x of n, have the same sign, so they all add together. And then by independence, the probability that they're all positive, well, that's 1/2 to the power of 7. And then the same for the probability that they're all negative. So the probability that S of n exceeds 1 in absolute value is twice this, or 1/2 to the power of 6. So this integral is 1 minus 1/2 to the power of 6 multiplied by pi, which comes to 0.984375 times pi. Okay, it's not as extremely close to pi as we had with Borwein's integral, but it's the same idea. And we can also compute Borwein's integral in a very similar way. It's a little bit more complicated, but still not too difficult. But I'll post the calculation on my blog and I'll link to it in the description below. Okay, let's modify Borwein's integral simply by inserting 2 times the cosine of x into the integrand. What difference do you think this makes? Well, let's look. First of all, it still integrates to pi, and then if we add in sinc terms, sinc of x over 3 still integrates to pi, sinc of x over 5 still integrates to pi, and as before we keep going, multiplying the integrand by more sinc terms, and it still equals pi, but this time we have to go all the way up to sinc of x over 113 before it eventually is not equal to pi. And its integral now, well, it's 0.9999999. Okay, too many nines to say. In fact, there's 137 nines times pi. What's going on here? Well, remember that cosine is the characteristic function of a Rademacher random variable, which is a random variable taking values plus or minus 1 with equal probability. So all we're doing by putting in this factor of 2 cos x is we're adding a Rademacher random variable and a factor of 2. But if you add a Rademacher y to the uniform distribution of x of 0, you get, well, what do you get? You get a uniform distribution from -2 to +2. I mean, think about it, right? If when y is 1, then it shifts x to be, or x of 0 to be uniform from 0 to 2. And if y is -1, then it shifts it to be uniform from -2 to 0. And you put them together, you get uniform from -2 to +2. So now the integral of our characteristic function, we get 2 pi multiplied by the probability density of y, which is 1 over 4, multiplied by the probability that s of n is less than 2 in absolute value. And so you get pi by 2 times this probability. That's the reason for also adding in our factor of 2 to make this integrate to pi. But summing 1 over 3 plus 1 over 5 plus 1 over 7, so on, how long does it take before this reaches 2? In fact, you have to go all the way up to 113. But let's look at something even more crazy. First of all, we didn't have to stick to odd numbers in Borwein's integrals. We could have looked at sinc of x over 2 times sinc of x over 3 and so on. These also equal pi, but they drop below pi once you get to the sinc of x over 4 terms, which is sooner, so it's less of a surprise. As it's 2025, let's suppose we insert a sine of 2025x over x term in here. And then we multiply by sinc of x over 2, sinc of x over 3, so on. Now these integrals, they equal pi. Again, surprise, surprise. And if we keep going, it still equals pi. How long do we need to go before it stops equaling pi? How many terms do we need? Well, this many. That's a number with 880 digits. In fact, that's how many terms in the harmonic series 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 and so on that we need to reach 2025. Now, as the estimated number of subatomic particles in the universe is only a number with 80 digits, then, well, good luck writing this down in full. Now here's a simple little identity that I saw on Twitter some time ago. But we've already seen that the integral of sine of x over x or sinc of x, that's equal to pi. But what about the integral of sinc of x squared? Well, using what we've discussed in this video already, you should be able to say that it's equal to pi times by the probability of a random variable uniform from -1 to 1 being less than 1 in absolute value. but that's always true. The probability is 1, so the integral is pi again. Taking higher powers of the integrand will drop the integral below pi, though. But then user addad8m asked this question in response. Well, we can say the answer to this is no. As soon as the first and second powers of f integrated from 0 to 1, as soon as they equal 1, then you know that all of the powers also integrate to 1. In fact, if u is a random variable uniformly distributed from 0 to 1, then the expected value of f of u is the integral of f, so it's 1, and the expected value of f of u squared is the integral of f squared, so 1 again. And then the variance of f of u is the expected value of its square minus the square of its expected value, or 1 minus 1, or 0. So it's got 0 variance, meaning that it's equal to its mean 1 with probability 1. So all powers of f of u have expected value 1. Okay, in response, I asked this question. Are the functions f and g on the unit interval so that the expected value of f times g to the power of n is equal to 1 for n equals 0, 1, all the way up to 2023, but so that the integral is less than 1 for all larger n? Well, here's my answer. You can pause the video and read this if you like, but I'll also explain it here. Well, let's bring the numbers up to date first. Is it possible for the integral of f times by the g to the power of n to equal 1 for n equal to 0, 1, 2, all the way up to 2025, but be less than 1 for all higher values of n? Now, this is a similar idea to the Borwein integrals, but one twist here is that I'll only look at random variables which take integer values. This means that they don't have a probability density, but the characteristic function still exists, and we can invert the characteristic function again to obtain the distribution, and it's even easier than it was for continuous distributions. In fact, the integral of the characteristic function of 2 pi u from 0 to 1, this is just the probability that x equals 0. To prove this, integrate the definition of the characteristic function. Commute the integral with the expected value, then you get the integral of e to the 2 pi I times an integer, and this is 0, unless the integer in the exponent is 0, in which case it's just the integral of 1, so it's 1. Okay, good. So now let x be uniformly distributed from minus 2025 to plus 2025, taking integer values. So that's 5051 possible integer values. So it's got probability 1 over 5051 of equaling each of the integer values in this range. And let y1, y2, so on, be independent Rademacher random variables. So they each take values plus or minus 1 with probability 1/2 each. Okay, the characteristic function of x, well, we saw this earlier, right? We can compute it. It's going to be sine of 2025 and a half x over sine of a half x. And the characteristic function of the yk, well, that's cosine of x. Now let's s of n be the sum of y1, y2 up to yn. This is just a simple random walk, a process which increases by 1 or decreases by 1 at each step with 50% chance each. Then the characteristic function of the sum x plus s of n is the product of the characteristic functions of all the independent terms making up this sum, or the characteristic function of x multiplied by that of yk raised to the power of n. Now let f and g be these characteristic functions suitably scaled. And as we saw, we just need to integrate to get the probability that x plus s of n is equal to 0, right? but x is uniform from minus 2025 to 2025. So the sum can only be 0 if s of n is less than or equal to 2025 in absolute value. And if it is less than this, then for each value of s of n, the probability that minus x coincides with this value is 1 over 5051. So the integral of f times g to the power of n is the probability that the absolute value of s of n is less than or equal to 2025. But s of n is a random walk, right? It changes by 1 at each step. It can't possibly exceed 2025 for n less than or equal to 2025. So the probability is 1. But then for all values greater than this, it can exceed 2025, so the integral drops below 1. Done. Now, all the calculations and the integrals, the Borwein integrals explained in this video, they could be done differently by using Fourier transforms and convolutions, which is effectively the same calculation. And this is the approach taken by 3 Blue 1 Brown in his video, which I will link below. But it seems a little bit more intuitive, to me at least, to look at the stochastic process approach, where you have a process and you can visualize, right, that it can't possibly exceed some level until some time when it can. Consider explaining this to a non-mathematician using the convolution approach. I mean, telling them that these integrals are equal to some convolution, and as you add more terms it always equals pi until eventually, for reasons, it doesn't. I mean, you're probably going to lose them pretty quickly. But in terms of stochastic processes, if you say it's equal to the probability, or pi times by the probability that the stochastic process doesn't breach a level, then they can see why this is constant. It's got no possibility of exceeding the level until you have enough terms, or you wait long enough that it can, and then your integral changes value. Anyway, please like and subscribe. I'm going to go away and create more YouTube videos until the watch time exceeds the threshold, YouTube monetization threshold. Almost surely.
Oh yeah, I'm almost sure.